Let's concentrate a bit more on the operating pressure. What is the significance of the operating pressure? The operating pressure is especially very important if I'm dealing with low Mach number compressible flows, because low Mach number compressible flows, because of this isentropic relationship, they are very susceptible to round off errors. So you get a term something like delta P upon P, which scales by Mach number square, and especially if it's a low Mach number, this quantity scales to a very low value. So in that case, if I'm using the absolute value of the pressure, which I'll be showing you what is the meaning of an absolute pressure. If I'm using the absolute pressure, this can be very high value. So what I usually prefer to do is to use the gauge value, that is the absolute pressure, and subtract the operating pressure from it. So I'm dealing with a very small value. So therefore this delta P upon P tending to 0 means this delta P does not get rounded off. So absolute pressure is defined as the operating pressure plus gauge value. So all the inputs that I give in Fluent will be in terms of the gauge pressure value. So this is especially important for reducing the round off errors which can be caused. You can also reduce the round off error, if you remember from the previous lecture, by using a double precision solver. So operating pressure has a great significance. It has great significance for reducing the round off errors, especially for low Mach number compressible flows. And in another case, when I'm using an incompressible ideal gas law for determining density variation with respect to temperature, that is the other case in which it's important to mention the operating pressure, because that operating pressure will be used for calculation of the density. Operating pressure is not so significant actually in high Mach number flows, or if let's say the density is being defined independent of the operating pressure. In that case, it can be a function of temperature or other functions. In that case, it's not really going to be used. So there are two specific cases in which uh, we should assign an appropriate and accurate value of the operating pressure. These are cases in which the Mach number is quite low and the ideal gas law is being used. Or in another case, let's say I'm using the incompressible ideal gas law. In that case, the mean flow pressure has to be accurately given as the operating pressure, because that will be used for calculating the density variation. If I include the gravitational acceleration effects, that's typically because of buoyancy driven flows. Now, buoyancy-driven flows are especially important when this ratio Grashof number divided by the Reynolds number square, if this ratio starts approaching unity, usually it's quite low. In that case, natural convection effects are not so significant, but if it approaches 1 or even exceeds, in that case, the natural convection effects are quite significant. Usually we define whether the flow is turbulent or laminar either by a Grashof number or the Rayleigh number being in this range of 10 to the power of 8. If it is less than that, it's usually a laminar buoyancy induced flow. Otherwise, it can start becoming turbulent. So usually in such cases, the gravity effect is to be included. And this can be done on the GUI of the operating conditions panel on ANSYS Fluent GUI. Um, the Boussinesq approximation especially, which we include, it is only valid when this term, the thermal expansion factor multiplied by temperature difference, is less than 1. If it is greater than 1, in that case we might have to have the density varying as a function of temperature completely. So Boussinesq approximation will not be used. But in the other case, let's say if it is if this ratio as if this value beta times T minus T naught, if it is exceeding the value of 1, in that case the thermal expansion coefficient multiplied by the temperature difference is quite significant, and the Boussinesq approximation will not hold then. And in that case, on the operating conditions panel, we also need to specify an operating density with respect to which the body force term in the momentum equations will be included. So that was all about the operating conditions. Let's have a look at the boundary conditions. I will be taking a dedicated lecture on boundary conditions, which is going to follow up, but let's have an overview. So basically we access this either through the define models, define boundary conditions option on the menu bar, or also on the GUI on the model tree. You can just click on boundary conditions and we can see the different boundaries that are available, and we can set up conditions for them. So basically there are a variety of options. We can have external faces for which we have to specify the boundaries. We can also have internal faces. Internal faces can be because of interior or two-sided walls, or in some cases we might have to generate an interface. And these are the different kinds of boundaries we have: inlet, flow boundaries, inlet and outlet, wall boundary, where fluid cannot flow but heat can. Symmetry boundary where flow is reflected as well as any other fluxes are reflected. Basically the gradient on a symmetry phase is zero. And we can also have the axis kind of boundary. So these things can be defined, changed, their type, and the specific values can be given on the boundary conditions option. Let's specifically have a look at how to deal with non-conformal interfaces. It can very well happen that you generate a structured mesh in one zone where it was easy, it was possible, and in the other case you generated an unstructured algorithm-based mesh. And in that case you want to bring the mesh together in ANSYS Fluent, and you want to generate an appropriate interface, especially in such cases like this one where you have some region where the mesh is not overlapping. So wherever it is overlapping, it will be treated as an interior, and where it is not overlapping, it will be treated as a wall. So what we do is these are the three steps that we follow for creating such non-conformal interfaces. We first of all read the grid into Fluent. Once we have read it, the different zone types, zone names are available in the boundary conditions panel. We change their type, the boundary type of these zones to interface. We say OK. Once we are done here, then we go to the define grid interface panel, which is also available on the tree. You can have a look at it, but you can also access it from the main menu bar, define grid interfaces, and we generate a name. We give a name, let's say grid interface, and we choose the two zones which have been actually defined in the boundary conditions. We change the type to interface. Usual practice is that we choose the smaller mesh size face, the first one, and the second one is usually the one which is a bit bigger. So this is the usual practice, just because of rounding off errors that can be reduced. So in this way you can also treat non-conformal interfaces. Let's move on now. After having set up the problem, defined what are the boundary conditions, what are the physical models, let's start solving the problem. So because Fluent uses a finite volume method to solve our problem, what we are actually doing is we are doing it in an iterative manner, because there is nonlinearity in the equations, which is being assumed to be a linear algebraic equation. Ultimately, using the finite volume method, that we are converting the nonlinear partial differential equations into linear algebraic equations, and we are solving the matrix. And in this case, it starts off with an initialization, and then it's an iterative process. So the initialization in Fluent can be done in three different ways. One of them is that the initialization can be done simply by giving a constant value in all the cell points in your domain. So that's the standard initialization which was available ever since the beginning of ANSYS Fluent, or Fluent as it was earlier called. And the other option that was included not so long ago was the FMG initialization, which is very helpful for compressible flow calculations, so that you can have a better approximation, better starting point. This has to be implemented using the text user interface. You have to type solve space init space fmg minus init. So this is all basically described. You don't have to write the whole name. You can just write fmg minus init, and it understands that it has to perform a full multi-grid initialization. This is a much better approximation. It solves an Euler equation, but the fmg initialization requires you to actually first of all do a standard initialization, and it will build upon that standard initialization and generate an FMG initialized problem on which you can solve the full viscous flow for your given problem. This is especially helpful because of compressible flows around airfoils, where there's a big domain around, and primarily the flow is inviscid in the bigger domain, and only close to the walls the viscous effects are important for capturing the shocks. In the release 13, a special kind of initialization has been introduced, which is based on solving the Laplace equation of the potential flow solver, and this is called the hybrid initialization. This is very helpful for increasing the turnaround time, reducing the turnaround time, making it faster to achieve convergence if you do an hybrid initialization. So this is very helpful. It's a new feature in ANSYS release 13, and how it is done is that we just choose the hybrid initialization option and we say initialize. We can also modify some settings by going to the more settings option which is available. Once the problem has been initialized, we move on to setting up the solver controls, how the finite volume method has to work. So we start setting up what are the different schemes, what are the Courant number, what is the under relaxation factor, how the phase discretization schemes have to define. So there are basically three steps in the solver controls, that how the equations have to be solved. First of all, we define which methodology, which solver has to be used, how should the equations be coupled. So you have the pressure based and the density based solvers. Within the pressure based, you have an option of a segregated solver or a coupled solver. So pressure based coupled solver couples the three momentum and one continuity equation together. That's the pressure based coupled solver. And the segregated solver solves each of the flow equations individually, and anyway the other equations like energy or species transport or turbulence model equations are all solved in a step by step fashion, that is the segregated fashion. But the density based solver, it couples the continuity, the three momentum and the energy equation. And if let's say we are also doing multi-species simulation, also the species equation are coupled together, and it forms a combined coupled set of equations which are solved simultaneously. So it requires a huge RAM space so that it can handle such a big matrix as it is generated. So the density based solver is especially helpful for compressible flows, highly compressible flows, and pressure based solver is usually used for incompressible or low compressible flows. The pressure based coupled solver is what ANSYS looks ahead to convert everything into the pressure based coupled approach and to slowly phase out the other ones. This is, by the way, the only option available in ANSYS CFX, but ANSYS Fluent has all the three options available. As far as the finite volume specifications are concerned, so it includes the phase discretization, and it includes options for choosing how the pressure and velocity equations, that is the continuity and the momentum equations, have to be coupled. And if it's, let's say, a compressible flow and I've chosen the density based solver, it also asks you for implicit and explicit choice here. We can additionally also include a pseudo transient approach to the, that is a time marching approach to the final solution, even if it's a steady state problem. This is a new feature in ANSYS release 13. More about this in the solver mathematics lecture. And the third step that is included in solver controls is to set up the solution controls. So how we set up the Courant number, or the different kinds of relaxation factors or under relaxation factors. So these specific inputs are provided at the solution controls panel. Once the solver controls have been set up, we move on to set up the convergence monitor. So this is how we will analyze whether the solution is converging or not. So we have options for monitoring the equation residuals. So as you can see here in this list here on this chart, these are the different equations like continuity, x, y, z, momentum, and velocity equations, energy equation is a bit blurred here, but what you can see are all the equations residuals are being reported here. This is one of the means to monitor whether my solution is converged or not, and you can set the criteria when I will accept my solution to be converged or not on the residual monitors panel on the GUI. So there are different options by which we can plot, we can monitor, we can store, we can analyze the progress of the solution. We can also set up some other monitors, like let's say a force monitor or a surface monitor, where we can see, okay, the temperature at this surface, when it becomes constant, I will say that my solution is converged. So we can set up these monitors, or basically there are three means by which the convergence is determined, and these are basically the equation residuals, which I've already spoken about. We can also set up some monitors like phase monitor, like say the temperature at the outlet, the average temperature, or the temperature at a point should not vary anymore, and then I say my solution is converged. And the third option by which we can assess whether the solution process has converged or not is to check for the imbalances in mass and energy. So we can check for the mass that is coming in, what mass that is going out, and the difference between the two, the net difference, should be less than 1% of the lowest mass which is entering into the domain. So this is a criteria which is defined in ANSYS Fluent for checking whether my solution is converged or not. Once I am analyzing whether my solution is going to be converged or not, I set up these monitors. I start computing the solution and monitor the progress. Now, computing the solution, as we know, basically ANSYS Fluent using the finite volume method is converting the nonlinear equation, especially which appears in the advection term, it's converting it into a linear algebraic equation. Now, when it converts it into a linear algebraic equation, the cost is that you have to do it in an iterative fashion. You have to solve the problem with an assumption and start iterating the problem, and we try to achieve a converged result where the solution is not changing anymore. So in that case, what we are defining are the number of iterations. This is the conventional method in ANSYS Fluent. But what has come up recently in the release 13 is the pseudo transient approach, which is basically inspired by CFX. So what you have in that case, we can approach it using a pseudo transient approach. In that case, I'm going in a time marching format, so I can specify my own time scale, which is this time scale is basically either can be user specified, or I can ask the solver Fluent to calculate this time step for me. And what I can do is I specify this time step and I start marching through the iteration steps. So iteration number of iterations are defined here. It's the same as the previous one, but I'm marching in time here. Especially for the coupled solver, the pressure-based coupled solver, this is very helpful to achieve quick convergence using the pseudo-transient approach. So solver basically tries to either meet this criteria of the number of iterations or the convergence criteria which you set up in the convergence monitors. So if the convergence criteria is met, it will stop the problem. If the convergence criteria is not met, it will iterate it as long as the problem is getting converged. Except for the unsteady flows. In the case of unsteady flows or transient flows, I specify a time step which is not a pseudo time step, but it is a real time. I'm marching in real time, so I'm specifying the time step within which it has to perform some iterations and try to achieve some convergence. So in that case, the solver tries to march in time and it tries to achieve convergence within each time step, either through the number of iterations, or it will try to achieve the convergence criteria which has been specified in the residuals panel. So overall, if you have a look at the approach that we have to have for solving a CFD problem, some fundamentals are very helpful. The basics that we have to follow as it has been described in the outline tree. We set up the problem, we set up the solution parameters, and we start off with a mesh. We start off with an initialization. We proceed either in time or through some or the other iterative scheme until we achieve convergence. So the problem setup and solver setup are usually project specific, although we can know that this is the usual practice, but there are no fixed values defined beforehand, but something which we learn through experience. We learn more and more with time what are the best practices for a specific class of problem, and with this we can become efficient users of this ANSYS Fluent software. I hope you could follow how we can basically go through the workflow in ANSYS Fluent, and this would help you very much to start off with solving a problem in CFD using the software ANSYS Fluent. I'm thankful for your attention, and stay tuned for the next lectures which are proceeding. The boundary conditions lecture will follow this up, and you will be in a position to set up a problem and do a simulation. Thank you very much for your attention again.